Our last example with spherical coordinates is to find the gravitational force of a hollowed out hemisphere, where rho is between A and B, on a point mass located at the origin. Assume the hemisphere has uniform density. We'll call that density delta. Normally we call the density rho, but we don't want to confuse that with the rho for spherical coordinates, so we'll call it delta. So here we're going to have a hollowed out hemisphere. So I'm imagining a hemisphere where we've taken out the hemisphere of radius A from a hemisphere of radius B. So I'm going to draw my hemisphere of radius B like this. And then I'm going to assume that I've taken out the hemisphere of radius A from the inside there. And we're going to ask, what is the gravitational force of that hemisphere on a point mass that's located at the origin? And I think the first thing that you have to do with this problem is that you have to understand that this point mass is going to feel a gravitational force only in the z direction. So if this hollowed out hemisphere is a large mass, then it should pull the point mass up toward or into that hemisphere. Okay, imagine we're not showing it, but this hemisphere, right, of radius A, right, has been hollowed out from the hemisphere of radius B. We're expecting our point mass to travel up this way. And the reason why is that the gravitational forces in the x and y direction are going to cancel each other out, okay? Because it can't be pulled to the left or the right, because the amount of force that it feels to, say, the left is going to equal that to the right. Same thing with forward and backward. So this is only going to feel a force in the z direction. So what we're going to say is that the force that it feels, it's going to feel in the z direction. So the force in the z direction, we're going to think about as being the magnitude of the total force that it feels, okay, times cosine phi. So remember that when we're dealing with spherical coordinates, if we want to project in the z direction, right, then we have a cosine phi. You might remember, right, that z equals rho cosine phi. So that means that the force in the z direction should be the magnitude of the force times cosine phi. So what we want to do is we want to add up a little bit of force that is directed from all different parts of the hemisphere, and add all those up in order to get the total force exerted by the hemisphere. So what we want is a little bit of force. So we're going to call that little bit of force in the z direction delta F sub z. And we're going to remember that that's going to equal the gravitational constant g times the mass. The mass is going to be delta times delta v, okay, times the point mass, which is going to be 1, and then divide by the distance, okay, and the distance is in fact going to be rho squared. Okay, so the distance of that point, right, from the origin, the point of the little bit, the distance of the little bit of mass that's in the hemisphere, some delta v, okay, is going to be rho squared. And then, of course, we're doing that magnitude times cosine phi. Okay, so just to remind ourselves, right, this is going to be the large mass, right? And that's going to be the point mass, which we're going to say has mass 1. Okay, so that means that the total force in the z direction, okay, if a little bit of force in the z direction is given by that function, the total force we want to integrate over our hemispherical region, that we want to integrate, say, g delta over rho squared cosine phi. And then for delta v, we're going to put in rho squared sine phi d rho d phi d theta. So this part here is the delta v. Okay, so summing that all up, we know that the rho is between A and B. This is a hemisphere, so we're only going to get the top half for phi, b being between 0 and pi over 2. And then we're going to get all the way around in the theta direction, so that's going to go from 0 to 2 pi. Okay, that's our force in the z direction. Okay, so our force in the z direction, we can again, essentially, we can bring out the theta integral. That's from 0 to 2 pi. We're going to integrate that d theta. I'm going to notice that the rho squares cancel. That's kind of cool. And so we also have an integral from a to b of just d rho. There's no other things that depend on rho. And then finally, we're going to get an integral from 0 to pi over 2 of our function of phi. That function is going to be sine phi cosine phi d phi. Now what I haven't dealt with is the constants, so I should have brought all my constants out front here. So my constants are g and delta. So let me put g and delta out front. Okay, so let's do a few of these integrals. So let's see, we're going to get g delta times the integral from 0 to 2 pi of d theta is 2 pi. The integral from a to b of d rho is just going to be b minus a. And now I'm going to use a trig identity. So I'm going to go integral from 0 to pi over 2. Sine phi cosine phi is actually, in fact, 1/2 sine 2 phi d phi. So I'm going to get, let's see, 2 pi g delta times b minus a. And then when I integrate, I'm going to get a minus 1/4 times cosine of 2 phi evaluated between 0 and pi over 2. Okay, so this is going to give me pi over 2. Going to multiply by that 1/4. G delta times b minus a. And then I'm going to be left with, let's see, minus cosine of pi. So that's going to be 1 minus a negative 1 for cosine of 0. So that makes 2. So when I multiply by 2, I'm going to get pi g delta and then b minus a. And so the gravitational force in the z direction, which is the only force that we're going to get that's non-zero, on that particle is going to be positive, notice, so the force is going to be pushing the particle up, and the strength of that force is going to be pi g delta times b minus a.